Hello, this is Physics 104B at Porterville College, Chapter 20 homework. We'll start with number 16. Number 16 asks about an electron and a proton. A certain distance apart, find the magnitude of the electric force between them. So asking for force, we're going to use Coulomb's law. We've got their distance is 52.9 picometers, that's times 10 to the negative 12. We've got the elementary charge, we've got K, we're going to use 8.988 times 10 to the 9th Newton meters squared per Coulomb squared. So we just plug that straight into Coulomb's law. The electron and the proton both have E squared. We're just concerned about the magnitude, so we're not interested in whether it's positive or minus, just getting the magnitude, and it's 8.24 times 10 to the negative 8 newtons. Number 18, bits of styrofoam, each carrying equal charges, repel with a force of 21 millinewtons when they're 15 millimeters apart. What's the magnitude of the charge on each, assuming equal charge? We're going to use Coulomb's law, but we're solving for charge. And so if you take Coulomb's law right here from number 16, assume that both charges are equal, so that'll be Q squared. And then you solve for Q. You get that Q is the square root of plus or minus times the square root of force times distance squared over K. Plug those numbers in and we get a charge of plus or minus 2.3 times 10 to the negative 8 coulombs. It's plus or minus, and from the given information we don't have the ability to solve for which one it is, whether plus or minus. Either way, as long as they're the same, they should repel. Number 21. An electron experiences an electric force of 0.61 nanonewtons. What's the field strength at its location? Electric field strength is force divided by charge that feels the force. So there's the force, 0.61 times 10 to the negative 9 newtons, divided by the charge of an electron. We get 3.8 times 10 to the 9th newtons per coulomb. Number 25. Negative 1 microcoulomb charge experiences an electric force in a certain electric field. What force would a proton experience in the same field? Alright, so we can look at this. First of all, the charge, and I've used the subscript C. The force on the charge, F sub C, is the electric field times the charge, Q sub C. Also, the force on a proton is that same electric field times the charge on a proton. So we can say the force on the proton equals, well, let's go back here actually. The electric field is, solving this equation, the electric field is the force on the charge divided by the charge. And so if that's the electric field, we're going to plug that in to this equation for the force on the proton. Force on the proton equals the electric field, which over here we said is force on the charge divided by the charge, so force on the charge divided by charge C, times the charge on the proton. And so what it comes down to, I've written it a little differently just so you can see that it becomes a ratio of the two charges times the charge C. When we plug in the numbers, we get the force on the proton is the charge of a proton, 1.602 times 10 to the negative 19 coulombs, divided by negative 10 to the negative 6 coulombs, and we get, times the force on the charge, 10I newtons. And that comes out to be negative 1.6 times 10 to the negative 12 I hat newtons. That is the force on a proton. So the proton going in the negative I hat direction. Here I've drawn it negative I hat direction, which then tells us, I haven't solved directly for the electric field, but you can see if that's the way the proton is going, being a positive charge, that's also the direction the electric field is going. The negative charge that was mentioned at the beginning of the problem would go in the opposite direction, the positive I hat direction. Number 26, the electron in a hydrogen atom, certain distance from the proton. What is the proton's electric field strength at this distance? So we treat it as a point charge. Electric field is kq over r squared. For probably I think the rest of this video I've taken to using for k just 9 times 10 to the 9th, or 9.0 instead of 8.988. But it's 9 times 10 to the 9th times the charge divided by the distance squared, 52.9 times 10 to the negative 12 meters squared, and you get 5.2 times 10 to the 11th newtons per Coulomb. Number 31, find the magnitude of the electric field due to a charged ring of radius A and total charge Q on the ring axis at a distance A from the ring's center. This formula has been derived, you can look back in your notes or in the book, from example 20.6 in the book. What we're looking at here is the charged ring with radius A, and we're specifically looking at the electric field a distance A, that same distance along the axis. So where x in this formula is the distance along the x-axis, we're just going to replace that with A. So we're going to let x equals A. And when you do that, it basically becomes a matter of simplifying. And you can see on this line, I've gotten kq over 2 square root of 2a squared. I think the book leaves it as the square root of 8 down in the denominator. I didn't want to leave a radical in the denominator, so I rationalized it, multiplying by square root of 2 over square root of 2. And so I got kq square root of 2 over 4a squared. And that is equivalent to what the book says, dividing by square root of 8. Number 32, the Millikan oil drop experiment. Small oil drop suspended in an electric field, field strength of 20 meganewtons per Coulomb. What mass drop can be suspended when the drop carries 10 elementary charges? All right, here's my force diagram on one of these oil drops. We've got its weight pulling it down, the electric field pulling it up, and we want to solve for where these are equal. So we say mg equals qe. Those forces are equal and opposite. And we're given that Q is 10 times the elementary charge. So we'll replace that with 10 little e times the electric field. Now we have mg equals 10 times elementary charge times electric field. And we'll solve for m by dividing by g. 10 little e big E divided by g. Little e, the elementary charge, is 1.6 times 10 to the negative 19 coulombs. The electric field we're given is 20 times 10 to the 6 newtons per Coulomb, and we end up with 3.3 times 10 to the negative 12 kilograms. Number 33 involves an acceleration. Accelerating electrons in an electric field of an X-ray tube from rest to 1/10 the speed of light in a distance of 5 centimeters. It's going to come down to F equals ma, but we need the acceleration, so let's go back up here. We have v naught is 0, v 1/10 of the speed of light is 3 times 10 to the 7th meters per second. Distance is 0.05 meters. We'll use our kinematic equation that says that acceleration is v squared minus v naught squared over 2 times displacement, and we get an acceleration of 9 times 10 to the 15th meters per second squared. Now we plug that into F equals ma, recognizing that the force on a charge from an electric field is QE. So we have QE equals MA, and we'll solve for that electric field. Electric field is MA divided by charge, where M, the mass of an electron, is 9.11 times 10 to the negative 31 kilograms. Charge is 1.602 times 10 to the negative 19 coulombs. And we get 51 kilonewtons per coulomb for the electric field. Number 37, two charges, one twice as large as the other, 15 centimeters apart. What's the magnitude of the larger charge? So we have these two charges. I'm going to label them as Q and 2Q. The larger charge that we're looking for is 2Q. Radius, there's force, so we'll plug into Coulomb's law. We have then Coulomb's law, when you take it through, becomes the force is 2K Q squared over distance squared. Solve that for Q, and you've got square root of R squared F over 2K, which becomes plus or minus 1.09 times 10 to the negative 5 coulombs. That's what Q is. That's the smaller charge. The question is asking what is the larger charge, so we'll do twice that, and it becomes plus or minus 22 microcoulombs. And there isn't enough information to say whether it's plus or minus, but that's okay because the question is asking what is the magnitude, so the magnitude would be 22 microcoulombs. Number 38. Proton is on the x-axis at 1.6 nanometers. So there's my proton with the plus E charge. I've done the tick marks every 0.5 nanometers, so there it is at 1.6. An electron's on the y-axis at 0.85 nanometers, and there it is with the E negative 1, or the negative E charge. Find the net force the two exert on a helium nucleus, charge 2e, at the origin. So there's my helium nucleus. I've drawn vectors showing what direction these forces are. The force from the proton, because this positive proton repels the helium nucleus, it'll kick it straight in the negative x direction. The electron, being negative, will attract the helium nucleus straight up in the y direction. We're going to use Coulomb's law for each force, and for the electron, we'll say the force of the electron, I'm using the vector notation here, is k times negative e times 2e over the distance from the electron squared, and using the vector notation, that vector is pointing in the negative j hat direction because the vector points from the thing that's causing the force, which would be the electron, pointing towards the helium, so that's in the negative j hat direction. And what you get is 6.39 times 10 to the negative 10 newtons j hat. The proton is, let's see, the force is k times positive e times positive 2e divided by the distance squared, and if we use the vector notation, we'll multiply that by the vector pointing from the proton to the helium, which is the direction my pen is facing, negative I hat. And so we get negative 1.805 times 10 to the negative 10 newtons I hat. So the net force is just going to be, since one's in the I hat, the other's in the j hat, pretty easy to do, we just say negative 1.81 times 10 to the negative 10 I hat plus 6.39 times 10 to the negative 10 j hat in newtons. If we want to know the magnitude and direction, you can use Pythagorean theorem to tell that magnitude. Use the arctan to find the angle, and you would get 6.6 times 10 to the negative 10 at a 106 degree angle, about the direction my pen is pointing. Number 45, Here we have a three-part problem. 65 microcoulomb point charge at the origin. Find the electric field at these three separate points. The first is 50, 0. I've labeled that A. Part B is 50, 50. And part C is 25, negative 75. You'll notice as I go through the solution that I've done A and then B and C in two different, slightly different ways, given what would be most convenient for this problem. So I did A using one formula, B and C I used another formula. And I used this different formula for B and C because being at an off angle, I figured this would be more convenient. But let's take a look at A. The electric field is kq over r squared times r hat. Now remember, r hat is the radial vector. We have k, 9 times 10 to the 9th, times q, divided by the distance squared, times, and we see going from the origin to A, that's in the I hat direction, so that I hat is r hat for part A. And so we get 2.3 times 10 to the 6th I hat newtons over coulombs. For part B and for part C, you can use that same formula that I did in part A, but then we'd have to do a little bit figuring out what r hat is. I have a better way. Instead of using r hat, I've substituted the r vector with its magnitude, recognizing that the r vector is the magnitude of r times r hat. So it's going to be in the same direction. It's just easier, I think, to do this problem using the full r hat. So here's how to look. If we make that substitution, kq, and instead of r hat over r squared, as in part A, it's going to be the r vector over r cubed. So k is 9 times 10 to the 9th, q 65 times 10 to the negative 6, and then we've got r cubed. So we think, what is the r vector? Well, the r vector, what is its magnitude? Looking back at the picture's off the screen. Okay. Looking at the picture, the r vector goes 0.5 I hat plus 0.5 j hat. So if it's 0.5 I hat plus 0.5 j hat meters, then the magnitude of it, which is r, is 0.5 squared plus 0.5 squared, the square root of that, but then we're cubing it. So if you take the square root of it and then cube it, you have to the 3/2 power. So in the end, the magnitude cubed becomes 0.5 squared plus 0.5 squared to the 3/2 power. Now we still have to deal with this r vector. What is the r vector? Well, very simply, that's the vector from the origin to point B, and so that's 0.5 I hat plus 0.5 j hat. Now, you don't have to solve it this way. You can use the method I used in part A to solve part B, and you can see for yourself which way you think is easier. So for part B, I get, when I solve all that out, we have this magnitude times 0.5 I hat plus 0.5 j hat. We should get 8.3 times 10 to the 5th I hat plus 8.3 times 10 to the 5th j hat newtons per coulomb. Part C, I've done in a similar way to part B. We have k times q divided by the magnitude of r cubed. So that's going to be 0.75 squared plus 0.25 squared. Square root that, but then it's r cubed, so we cube it, and in the end, square rooting and cubing puts it to the 3/2 power. And then we're going to multiply by the r vector, which is 0.25 I hat minus 0.75 j hat. So we get an answer of 3 times 10 to the 5th I hat minus 8.9 times 10 to the 5th j hat newtons per coulomb. Number 60 involves an electric dipole. In an electric field, a dipole with dipole moment 1.5 nanocoulometers is oriented at 30 degrees to a 4 meganewton per coulomb electric field. Find the magnitude of the torque on the dipole and the work required to rotate the dipole until it is anti-parallel to the field. Alright, so I've drawn it at about a 30-degree angle. You can see it's going to get torqued. It's actually going to be pulled to align with the electric field, so in this case clockwise. The torque on it is the electric dipole, the cross product of dipole with electric field. If we want the magnitude, we can say that cross product is P times E times the sine of the angle between them. So you're given P, you're given E times the sine of 30 degrees, and you should get 3 times 10 to the negative 3 meters newtons. Part B asks, what if we want to turn it against the way the electric field is torquing it? We want to turn it counterclockwise so that it's in this configuration, so that it's anti-parallel, meaning it's got a 180-degree angle with the electric field. So we use the formula that work is the integral from 30 degrees to 180 of torque d theta. Torque, remember, is PE sine theta. As we take this integral, P and E are constant. They can go out to the left. We've got PE times the integral of sine theta d theta. That becomes a negative PE cosine theta from 30 and 180. And so you plug in the numbers and you should get 11 millijoules. Number 69, the last problem of the set. A straight wire 10 meters long carries 25 microcoulombs distributed uniformly over its length. What is the line charge density on the wire? Find the electric field strength 15 centimeters from the wire axis, not near either end, and 350 meters from the wire. Make suitable approximations in both cases. Well, for part A, the line charge density is Q over L. That's 25 microcoulombs per 10 meters, or divided by 10 meters, which is 2.5 microcoulombs per meter. For the next part, from example 20.7, the electric field, we are going to be assuming, if you look back at 27, and you notice in the book that it said make suitable approximations. What we can do is use this equation that the electric field is 2k times lambda divided by y, where y is 0.15 meters. When we're that close, we can use the assumption that it's an infinitely long wire. So you plug in the numbers as you see on the screen. And you should get 3 times 10 to the 5th newtons per coulomb. It assumes an infinitely long wire. And for this distance, that is a close enough approximation. Now, part C, we are very far away from the wire. It's a 10-meter long wire. We are 350 meters away. This is actually a scale drawing where this line right here is my 10-meter long wire. This is 350 meters away. We want to know what the electric field is. And what we can do is actually approximate it as a point charge. We are far enough away that that approximation will work. So we can say the electric field is, and again we are approximating a point charge, so it's kq over r squared. 9 times 10 to the 9th times the q of 25 times 10 to the negative 6 coulombs divided by 350 meters squared, and we get 1.8 newtons per coulomb. That is the end of the chapter 20 set.